Hello, the first module that I would cover in ME 571 Reliability in Engineering Design is the introduction module. In the introduction module, I will motivate the notion of reliability. What is reliability? I'll explain the reasons why we have concerns about reliability or why we need to study reliability. And I'll also give you a case study from my research experience involving reliability. So again, like I said in the description and procedures, I'll be breaking each module into sub-modules. So module 1.1 is really the introduction, conceptual introduction, and module 1.2 is the case study that I will go through in depth. So let's start with module 1.1, which is the conceptual introduction. We will begin with the question, what is reliability? And before I answer the question, what is reliability, I will start with the observation that if I take a product, a mechanical or electronic or aerospace or civil, any system, any physical system, what we notice is that failures don't occur at a precise time. So there is uncertainty, there is randomness, if you will. Not entirely random, but there is uncertainty. And if failures were to occur at a precisely predicted time or expected time, we would call that a deterministic failure mechanism. But that doesn't happen very often in any physical system, automotive, aerospace, electronic, any physical system. Things don't fail at exactly the same time. And the reason for that is uncertainty is inherent in any engineered product, and there are many sources of uncertainty, but the primary sources, three primary causes, are geometrical variation. Part to part geometrical dimension may be different. The same material, nominal material, might have different strengths. So the material behavior may be different. And that's something that we know when we test materials. We don't always get precisely the same strength. We have a variation about some expected value. And there's also uncertainty in loading history. If I take an automotive system, I may not always drive on well-paved roads. Sometimes I might drive on roads that are not as well paved. The planes may not fly through the same conditions. Sometimes they fly through turbulent atmospheric conditions. So that leads to differences in load history. So given this, reliability is the probability that an item will perform a required function without failure under stated conditions. This is important. The stated condition, this notion of stated condition is important. Under stated conditions for a stated period of time. So reliability is the assurance from a product developer point of view. It's the assurance that the product will perform the required function without failure under the stated conditions, under the prescribed conditions for a period of time that's specified by the product developer. So why should we study reliability? We want to study reliability because we want to reduce or prevent likelihood of failures. We want to assure that our products are good and worthy of purchase. And if failures were to occur, we want to understand what caused them and how to prevent them from happening again in a current or future product. And if failures are likely to occur, and it's a critical part, we want to be able to cope with those failures if it's a critical part. If failures are possible, we want to be able to cope with failures. We want to build in redundancies, for instance, or we want to account for the fact that it's a critical part with strong liability issues, then we might want to design it in a special way. So redundancy is one common way to do that. And we also want to analyze past reliability data to be able to estimate reliability for new designs where we may not have enough data. So we want to be able to understand and analyze failure data. Ultimately, what we really want to do is design to ensure reliability. That's the reason why we want to study reliability in this particular course. Often, examples of what I mean here in terms of analyzing reliability data. So here is an example of that. This is again from my research. I'll discuss this in case study in more detail. So here was an electronic component assembled onto a circuit board, and it was tested by a special technique that we had developed in my lab called simulated power cycling, using a Peltier heater to heat this component from an external source. And when we do that for many components, and these components are assembled onto circuit board using two different types of solder alloys, tin 3.0 silver 0.5 copper alloy, as well as tin 3.8 silver 0.7 copper alloy, what are popularly called SAC 305 or SAC 387 in the industry, the electronics industry. And they were tested for with different what are called dwell times. They go through a temperature ramp up, hold for some period of time, temperature cool down, hold. So these are the hold times are what are called dwell times. And these were tested with different hot dwell times. What you find is the failure times are all the same, nominally identical components assembled with identical materials, and you find that the failures occur at different number of cycles. And this is what we mean by an inherent uncertainty in failure times. And this is the percentage of components that have failed. So the questions that arise when you do these tests is, how many components should I test? How do I characterize these uncertainties? So those are all questions that arise. And then we want to know if a particular model that we have fit, like this line here, is that a reasonable fit for the data that we see here? Or should we have used a different model? So is this a reasonable fit? Is this a reasonable fit? These are all questions that arise, and those are questions that we will address in this course. Okay, how to go about fitting this data, how to analyze, how to determine whether the fit is a good one or not good. So we'll learn to do that in this course. What we won't do in this course is what's called post-failure analysis, where we study in depth the failure phenomena to understand the physical causes of failure. Here, for instance, what you're seeing is the initiation of a crack and growth of the crack in the solder joint. What you're seeing here is a cross section of the solder joint in the assembly of this component here. This is on one side of this solder joint is the component, on the other side is the circuit board. And what you're seeing here is the initiation and growth of the crack. And this requires understanding, and studying this requires more detailed physics than we would have the opportunity to do in this particular class. And here what you're seeing is a snapshot midway through the cycling process. Cycling was stopped. Ink was injected, dye was injected, and then the cycling was continued. Ink was injected, then this testing was continued, and eventually the crack went through the entire solder joint. But you can mark the location up to which the crack had grown when we had stopped to inject the dye. Then further, you can look under a scanning electron microscope to try to understand the morphology, the surface morphology. This level of detailed physics is beyond the scope of this class. So we will learn the statistical techniques in order to characterize the failure, but not so much the detailed physics that follows the statistical analysis, because this is a little bit more specialized and more advanced than what we would than the background that we would need for studying the statistics. As with any system, both these approaches have to go hand in hand. If you rely entirely on a statistical approach, then you will need a lot more samples. And if you use a combination of both statistical approach as well as physics-based understanding of what caused failures, then fewer number of samples are sufficient to explain why something failed and how to correct them to prevent this sort of failure mechanism in future. Why do products fail? Well, the first is poor design, inherently incapable. And this is really the cause that we will address in this particular class. We want to ensure that our designs that we produce meet our reliability requirement, and the tools and techniques to do that is the focus of this particular class. The second reason why products might fail is overstress, unanticipated loading. Related to this, I want to show you a little video clip.
All right.
No, you gotta go. Belichick is so upset about the big play.
Here it comes. He threw it on the ground.
And he threw it up.
He threw it up in the stands.
Receivers 5-6 yards down.
All right.
No, you gotta go. Belichick is so upset about the big play.
Here it comes. He threw it on the ground.
And he threw it up.
He threw it up in the stands.
Receivers.
So what I showed you there is a Surface Pro tablet that in the heat of the game got thrown, and that was a tweet from the VP who was responsible, VP of Microsoft, who was responsible for building Surface products. So they were very proud of their product. It actually survived. It turned out the Surface Pro tablet that was thrown into the stands, which was thrown to the ground and thrown into the stands, actually survived. But that is not a design scenario. You might have users that abuse your product. That's an overstress. That's not a design scenario, but it happens. And in this particular case, the product survived. Products are not designed to survive that sort of abuse, but it survived in this particular case. And the other failure cause is uncertainty in load and strength. Okay. And this is something that we want to account for in the design phase. We want to account for uncertainty in load and strength in the design phase. However, when we do design, we may not have all the information that we need to characterize the uncertainty in load or strength. So, however, we might progressively improve based on improved information that we would have. The other cause, and this is really related to uncertainty in strength, is the degradation with time. What do I mean by that? All materials degrade in strength with time. And I'll explain that in more detail later, but all materials degrade with, the strength of all materials degrades with time. And the reason for that is thermodynamic, and we'll discuss that in detail later. So let me talk about uncertainty in load and strength in a little bit more detail, and as well as degradation of strength with time in a little bit more detail. So you want to take all of this into account to ensure that our design meets our reliability requirements. So if I have a deterministic design, a traditional design point of view, we have load as one fixed value, strength as a fixed value, and then we apply a safety margin or a safety factor to make sure that load is always less than my strength. Okay, that ensures that we have a reliable product. However, what we don't know is we still might have failures. You cannot completely eliminate failures, but we might have over-designed our product. And we don't have control over the number of parts that might fail. So we would have over-designed more expensive product, and we don't have control over the number of parts that might potentially fail. So here is another situation where the load is uncertain. We might characterize this uncertainty. And strength is deterministic, and you have a safety margin. It might be smaller than what we have previously, because what we did previously is we lumped all our lack of understanding of the distribution of load and strength into a safety margin, a large safety margin. Here you might be able to get away with a smaller safety margin because we have a better understanding of uncertainty in load. And similarly, if I have an understanding of uncertainty in strength, I might be able to get away with a smaller safety margin. Finally, if I have both uncertain load and strength, then what I can characterize mathematically is the population that is at risk, that's at this intersection of load and strength. And controlling this population assures me of the reliability that I seek, and that is an important goal of what we'll learn. So that's about uncertainty in load and strength. The other point that I mentioned previously, was the degradation of strength with time. So initially, load and strength might have this sort of a distribution with this population at risk, the intersection being a small region here that has products that are at risk. But what happens is the strength usually degrades with time, and examples of such degradation include creep, fatigue, oxidation, corrosion, etc. These are all thermodynamically driven phenomena that cause strength degradation, and as a result, the population that's at risk increases with time. So what we want to again be able to do is to understand these mechanisms, understand that these mechanisms exist, and as a result, load and strength interference the population, at-risk population, which is the load and strength interference region as it's called, and that might increase with time. You want to account for that during the design phase, so we design products that function at the required time for as long as we need them. Thank you.